So I want today to talk about, to finish giving the explanation of why that one map that we looked at in the Freudenthal suspension theorem would be an isomorphism, or conditions for when it would be. And the reason that, so as an editorial aside, it might have seemed strange that if I give 4 talks, I spent an entire day doing what seemed like a fairly technical argument with the Freudenthal suspension theorem. And the reason is all of the steps in that argument are prototypes for the kinds of arguments that you make time and again in equivariant homotopy. That at the end of the day, I want to understand equivariant maps between two things. So I try to say, to what extent is that the same as some sort of non-equivariant maps? So maybe between the maps between the fixed points, which is what we're going to end up looking at today, or just underlying maps. And the whole argument proceeds via induction along the cells. I figure out what are the stabilizers of a particular cell, how do I write it as G mod H plus, smash a disk. And now I've reduced the problem to an H equivariant problem, and so I could say, by induction on the order of the group, I understand what happens. Because I have sort of 2 different kinds of inductions that I can run, those along the dimension of the complex and those along the order of the group. And so those are the 2 pieces that are really going into this argument. And so that's why I felt it helpful to spend some time on it. Do you have a question? Okay. All right, so at where we left off, I wanted to look at maps from SK into loops V sigma V. Y versus, I'm apparently writing this diagram backwards, SK into Y. And I wanted to know, when is this map an isomorphism? And I used a few adjunctions to convert this to SK plus V sigma V Y, and then the H fixed points of that, and then I applied the restriction map along the fixed points of SVH to now sigma VY H. And this was always isomorphic to non-equivariant maps from SK plus VH into the VH fold suspension of YH. And this was always isomorphic to SK into loops VH, sigma VH, YH. And then when I traced around the composite, using that this was SK into YH, this was the ordinary Freudenthal map. So this is the map that I wanted. This is the one that we understand the connectivity of by the classical Freudenthal suspension theorem. And so we reduced it to understanding, when is this map an isomorphism? So that's just a quick refresher for where we left off. And so now I see this map is induced by the inclusion SK plus VH sitting inside SK plus V. And so I want to know, when does this inclusion induce an isomorphism on homotopy groups? So if you looked at the problems that I wrote up yesterday for the problem session, one of them was a concrete instance of this. I asked you to look at the case of V as the sign representation for C2, and then see, when does this map become an isomorphism? And I even sketched out how you're supposed to think about it. Namely, I want to understand the fiber of this map, or write this map in a cofiber sequence, and then also take the cofiber of that. So let's look at the sphere of V. And if I look at the sphere of V, I want to actually, I'll do this one. So if I take the sphere of V and add a disjoint base point, I can map this to the zero sphere and via the obvious non-trivial pointed map. In fact, there's a unique non-trivial pointed map. And then I can take the mapping cone of this, and I get the V sphere. So one of the ways that I can understand how these fit together is using this sort of sequence. So now let's assume that the G fixed points of V are 0. And so what does that mean? That means if I take fixed points of this diagram, I again get a cofiber sequence. What are the fixed points of the zero sphere? The zero sphere. I have 2 points. Both of them are fixed. So by definition, the fixed points are those 2 points. So this is, again, the zero sphere. What are the fixed points of the V sphere? It's again S0. I have 0 in the point at infinity. If I'm not at the point at infinity, then the V sphere looks just like V. And so I'm asking, what are the G fixed points of V? And I already assumed that the G fixed points of V were 0. So this is also the zero sphere. And what's this map? Is the identity. So this took the base point to the base point, which went to the point at infinity. And then the cone point got identified with the origin in V. And so I can even draw a picture of this. Imagine this is the sphere in V. Then I put in a cone on that, and then I have my disjoint base point. What I'm supposed to do is put the cone on this, and I'll just put it filling in the inside. And then I also have the part that connects down to the base points, the one at infinity, and that just filled in the rays outside. And that's my identification of the mapping cone with the V sphere. And so I see that the other point went in as the origin. So what does that mean the fixed points of this are? Well, this is a cofiber sequence, and this part's the identity. So the only way I can do that is if this whole thing, the fixed points, are a point. Because I know that the mapping cone of something contractible going to a space is the same as the space again. So this guy is just a point. Another way to think about it is the unit sphere in V has no fixed points. Could I see that another way? Could I have done it without using this cofiber sequence? Or could I have shown it more directly? Well, the points here are the points of distance 1 from the origin. And we already argued that the only fixed points, are the origin. So in particular, the origin doesn't have distance 1 from itself. So none of these sit in the set of fixed points. And so I would deduce more directly that the fixed points of that is empty. All right, so if I build a GCW structure on this, it has no fixed points. So that means that all of the cells are of the form G mod H plus smash a disk for H a proper subgroup of G. If I had cells, or better said, I can choose a cell structure so that these are all the cells. I mean, obviously, I could put in a cell that's not really attached to anything, and then that's going to be just a contractible piece. So the ones that, if I actually have something that's homeomorphic to this, I only get cells with proper stabilizers. So passing through this cofiber sequence then, everything here has a proper stabilizer. This is the zero sphere. That means the difference between this as a GCW complex and this as a GCW complex are cells with proper stabilizers. And in fact, I know what those cells are. If I choose a cell structure for this, then the cells that I see here, the zero cells are S0, and the K cells here are the K-1 cells here. They're just the suspensions of the K-1 cells here. So a cell structure of this gives me a cell structure of this. And all of the cells except the zero cell are induced. All right, so what does that mean? Let's say, again, so back to the proof of the theorem. If I have some subgroup, K of H, such that the H fixed points of K are properly contained, the H fixed points of V are properly contained in the K fixed points of V, then we have cells, or really we could have cells, of the form H mod K plus smash a disk for R between the dimension of the H fixed points and the dimension of the K fixed points. The idea is, when I look at the K fixed points, that's again a sphere, and I have to put in cells which are fixed by K, but not fixed by H. And so I put in those cells, and the harshest way I could do it would be if I had cells in every dimension that actually had stabilizer K. It could be that, in fact, the K fixed points were also the K prime fixed points for some yet smaller group. In which case, I would really be seeing H mod K prime cells. So this is a super harsh assumption. I've put in the worst of all possible scenarios. For every subgroup of H for which I have a bigger set of fixed points, I actually have cells. So now let's think of what that means back here. I want to start putting in those cells one at a time. And so if I want to add a cell, then I'm going to look at H mod K plus smash, and then the appropriate suspension, so the K-fold suspension of all of the disks that showed up. So that's S K plus R minus 1. This is my attaching map that goes in to the K minus 1 skeleton, to the K plus R minus 1 skeleton of S K plus V. And then I would map to the next stage attaching that disk. I'm sorry. So I'm now, as opposed to putting in all my cells at once, I'm saying let's put them in one at a time, because it'll be easier for us to analyze what's happening. This gives me a cofiber sequence, because I've attached a single cell. Maps out of this gives me an exact sequence. In fact, the next stage then, if I take the mapping cone of this map, it's just h mod k plus smash the k plus r sphere. So if I map this into the v-fold suspension of y, I want to keep this up for now. At this point, I assume that I've built a certain amount of the skeleton.
Okay.
And so I'm attaching the next cell.
Okay.
So I should make that clear. I'm going to now run an induction argument
So
to induct over all of the cells.
Okay,
And so
in that dimension, we're looking at the cells that are being attached. Okay.
exactly. So I'm going to assume that the map to here, the map comparing the k plus vh fold, the maps out of k plus vh into the v-fold suspension of y, to maps out of the k plus r minus 1 skeleton is an isomorphism. So I want to know, when is the map induced by this inclusion also an isomorphism? Thank you. And so I get a condition. Here, I have a cofiber sequence. And, well, really, this is the piece of the pupa sequence. And I want to know, when is the map in homotopy induced by this an isomorphism? Well, I have h mod k plus smash s k plus r minus 1 into sigma v y. And these are, again, the H equivariant maps. At the other extreme, I have the suspension thereof. And then I have the two pieces that I want. So that one's a little hard to write, or in this space. So I'll just call this one x for now, x1 and x0. So one of the ways I can force that middle map to be an isomorphism is for both of these sides to be an isomorphism. Or sorry, both of those to be 0. That's the word I was looking for. 0, not isomorphism. So this, by our adjunction, this is sk plus r mapping into sigma v y. And this is the k equivariant maps. And so this one is sk plus r mapping into the vk fixed points of yk. Yeah?
Should the arrows be going the other way?
Yes. Yes, thank you. Okay. What do I know about the connectivity of this? Well, in fact, the connectivity of the v-fold suspension is exactly dimension v to the k, well, minus 1, because it's a sphere. So this part contributes dimension v to the k to the connectivity. And what do I know about r? Well, this r I've actually managed to hold fixed, and r is at most the dimension of v to the k. So this side, this is the dimension of v to the k plus the connectivity of y to the k connected, which is then bigger than or equal to, well, r, well, I'll just leave it at that. So then as long as k plus r is less than this number, this group ends up being 0. And same thing over there. As long as k plus r minus 1 is less than or equal to this, I get 0. So that provides for me a bound on k. We have a bound on r. Namely, the bound on r is dimension v to the k. So the biggest possible thing, the worst possible scenario, is if r is dimension v to the k. That's going to make this side as big as possible compared to this one for r. On the other hand, then I have k plus r is supposed to be less than or equal to the connectivity of this. So dimension v to the k plus the connectivity of y to the k. Both sides include dimension v to the k. So I can guarantee that this is 0 if k is less than or equal to the connectivity of y to the k, then this is 0. Because this guy is dimension v to the k plus connectivity of y to the k connected. This guy is that k plus something smaller than dimension v to the k sphere. So I get that. So you'll notice I said that I'm going to finish proving the theorem, and I even set up there a proof of the theorem, and I never actually stated the theorem as to the connectivity. Because if I just stated the theorem, it wouldn't be as illuminating. I would have deduced 2 criteria. I would have deduced this one. So k has to be less than or equal to the connectivity of y to the k whenever I have this condition. And then if I have these 2 pieces, then this maps an isomorphism. So let me name them. So here's box 1, and here's box 2. And so I'll say, if whenever I have box 1, we also have box 2, so in other words, k is less than or equal to the connectivity, then this is an isomorphism. That's what we've shown. So we want to understand this, and I've given you a super harsh condition for it. Now, when was this one an isomorphism? Well, this one was an isomorphism whenever k, well, I had 2 things. First, I needed that if VH was 0, then there was nothing to do. And second, if VH is non-zero, then I needed K to be less than or equal to twice the connectivity of YH. And so now in this horrible rhetorical abuse, now I can state the Freudenthal suspension theorem, because I can show what we've actually proved. The map from Y to loops V, suspension Vy is K connected where I have the following conditions. K is less than or equal to twice the connectivity of YH, and K is less than or equal to the connectivity of YK for all K proper subgroups of H for which I have this criterion. All right, so you see, this is what I meant when I said I have to use a bunch of the sort of techniques. I used induction along a skeleton, which of course we know from ordinary algebraic topology. I also ended up comparing the value at subgroups. And I get this curious relationship. Here, I get the expected thing, that it's about twice the dimension connected. Here, I get a really different condition. Now, this actually isn't as terrible as it seems. This one looks like it's a linear connected condition. In fact, well, both of them are linear conditions. But this one looks like the connectivity of Y rather than twice it. The good thing in the cases that we'll end up doing, I want to make this grow very fast too. So one of the ways I can make this grow very fast, in other words, I'd like to say that the connectivity of Y to the KH should be on the order of twice the connectivity of YH. And one of the ways I can do that is by making the dimension of this significantly bigger than the dimension of this. In fact, make the dimension of this grow as a multiple of the dimension of this. That will then help me control the size in the way I want. Okay, so why stabilize? Or why would I choose different V's? Now we have this fairly complicated condition for when things stabilize. But it's not difficult to show that if I include trivial summands in V, then it always automatically stabilizes because I start putting in bigger and bigger things. So I'll leave that to you to think about. But let's get some much more interesting consequences. So first off, let's just think of what the inclusion of the trivial representation in my universe does. Well, on the one hand, it means that all of my Hom objects are in fact abelian groups and compositions bilinear. So all of the things that I would want. Second, it means that, well, I know that if I map out of a wedge, I know that this is the same as the direct sum of the individual factors. But then the more surprising part is that this is also, and that's not going to be the way to do it. It's also the case that maps into the wedge are the direct sum of the factors. So in other words, wedging things together is both the coproduct, that's this statement, and the product in this category. So finite products and finite coproducts agree, is another way to say this. And then in the similar spirit, I can make the same statement about cofiber sequences and fiber sequences. So in other words, I know that if I map out of a cofiber sequence, then I get a short exact sequence. If I map into a fiber sequence, I get a short exact sequence. This says that I can also map out of a fiber sequence or into a cofiber sequence, and I get the same short exact sequences. And then the last thing that I observe is I can make sense of maps from the k-fold suspension of x into y for any integer k. For natural numbers, it's obvious what I would do, because the suspension of x is, again, a finite CW complex, and I've already defined what it does on finite CW complexes. The important part here is I can also allow negative suspensions of x. I don't have something that would make sense here. There isn't a finite GCW complex that's the -7th suspension of the zero sphere. Spaces have no negative homotopy groups. But I can make sense of this expression where I would just define this to be the same direct limit of the v plus k-fold suspension of x into the v-fold suspension of y. I'm sorry. And now, if I take just those v that contain k copies of the trivial representation, or for negative, it would be minus k copies of the trivial representation, then I can subtract away k trivial representations from v if v is sufficiently big. That doesn't change the value of the direct limit. By taking the direct limit over all of those things that contain k trivial representations, that's the same as taking the direct limit over all of those things, because contains k copies of the trivial representation is cofinal. Everything sits inside something that contains k copies of the trivial representation. So now I get a graded abelian group of homomorphisms. So I can make sense of and then this has a grading. So I'm out of slots, so I'll put it here. Graded abelian groups. And all of the sequences that I see, in fact, give me long exact sequences for the graded abelian group context. All right. Okay. So this was just including trivial representations. So to talk about what I get for the non-trivial representations, I'm going to describe for you a map. So if an orbit, G mod H, embeds into V, so this is a G equivariant embedding, then we get a Tom collapse map and it's of the form SV maps to G mod H plus smash SV. So this is actually the usual Tom collapse. So what do I mean by that? If you give me, say, a set of points in a vector space, or in fact a submanifold, if I do that, then I can take the normal bundle to that collection of points. That gives me, and then take the disk bundle in that normal bundle. So it gives me a bunch of little disks about each of my points. And what I can do is I can take and map the one-point compactification of V to the map that crushes the complement of all of those little disks to a single point. That's this one. Yeah?
So if we're just going to do this as an ordinary CW complex, it would look something like a bouquet of spheres, and
Mhm.
there are going to be cardinality G mod H above.
Mm-hmm. Mm-hmm. Exactly. So if I think of it just in that case, I've included G mod H points into V, and I've Tom collapsed on that, so I get a bouquet of G mod H spheres. And all I'm saying is, since this was an equivariant embedding, my little normal bundles also move around each other, and I get this. So let me draw a picture.
Could be sort of like a slice theorem for like these compactifications? Like the slice in this case is the compactification of V?
I don't know in what sense you're using the word slice there.
Or sort of like the normal part of the orbit?
I don't know, so
Well,
let's
think about it.
let's talk about it afterwards. I mean, maybe I just haven't thought of it that way, so that'd be neat. All right, to shake things up, I'll do a bigger group. I know, a much bigger group. And I described a representation, which I'll call it lambda, and this is just the complex numbers, so R2 plus rotation by 120 degrees. So here's the origin. And then I need to choose an embedding of C3 inside there, so I'll put it in as the third roots of unity. So there's one, about here's another, about here's another, ish. Wow, that wasn't as bad as I thought it would be. And so what I do is I choose a little disk about each of these, and I choose the little disk so that the disk about this one, when I apply the group action, gives me the disk about this one. When I apply the group action, gives me the disk about this one. All right, so in other words, I've chosen an equivariant normal bundle. Now, my Tom collapse is the one that sends all of the orange stuff goes to the base point, and I'm left with a little bouquet of spheres. Now, I've claimed in my Tom collapse that I get actually the V sphere over here again. So that's the only part that's perhaps non-obvious in this. Why is that I'm getting the V sphere again? In other words, when I take this little disk, I don't see that this is a copy of V equivariantly. In fact, it can't be a copy of V equivariantly. If it were, then when I apply the group action, it would just move amongst itself. But I know that when I do the group action, it moves over here. On the other hand, what do I know? I know that, I wonder if this will show up. If I look H equivariantly, then for h that h, then this point is fixed. This is the orbit corresponding to EH in G mod H. H fixes this. So H equivariantly, this has to be a fixed point. The origin is also a fixed point. So the line through this has to be entirely fixed. It's a representation, so it acts linearly. So what I can do is I can take this point, or this little neighborhood, and H equivariantly translate it back to the origin. So this doesn't look like a representation of G, but this is a copy of the representation of H, IH upper star of V. Because I could have just translated that point and say that fixed point is the origin and just pull everything back along the line from the origin to that point. So if I do it this way, then my Thom collapse has the following form. My Thom collapse really looks like I take the V sphere and I send it to G plus smash over H with the restriction to H of the V sphere. So in other words, it really maps it to the induced V sphere. And that I can see fairly straightforwardly. If I look just H equivariantly, I've collapsed this down to a point and I got the IH upper star V sphere. And then what did the group do? It took that one and it just translated it around to their copies. So yeah.
So this is like silly though, because there's not very many subgroups, and so.
Well, I'm using the fact that I can actually explicitly draw the C3 case to give you intuition for
Okay.
what you should be thinking for the general case.
Okay. Well, can you explain the action of H on the Thom collapse in the cases where H is either G or trivial, or is there no?
If H is G, then this is the identity map.
Yes. Okay.
Because I can choose the origin,
Sure.
and then a disk about the origin is the unit disk in B. If it's trivial, then I've had to put in just a bunch of different copies,
Yeah.
and I'm asking, you give me a point and then a neighborhood about it with no equivariance.
Okay. Sure.
Because by this argument, this is fixed by E times the identity. Well, everything's fixed by the identity. So I can take any of my points and translate them back. And the group is just permuting the pieces.
Sure.
So the same thing's true if I do G mod H, where now this is EH. I identify it with a disk in IH upper star V. And then when I Thom collapse, that piece becomes the IH upper star V sphere. That's this one. And the other pieces are the G translates.
So could you kind of see it like the tetrahedral group acting on R3? If they have a vertex of the tetrahedron, can you kind of see what's going on? Like a non-trivial subgroup there? Because it rotates on an axis.
Mm-hmm.
Is that kind of what's going on? Because I can't like really see how H acts on neighborhood here, like she said, because there's nothing to do. So I'm trying to, is there a picture in R3 you can draw with a non-trivial subgroup that gives some insight?
There's two questions there. Is there a picture I can draw? And is there one that would give insight? And I think you're right that choosing a bigger group would allow a different description. It's a question of whether or not I can draw a bigger group.
But you did C4.
Four on R2.
Yeah.
Oh yeah, then we'll just flip the thing over.
Yeah.
Okay.
Yeah.
Yeah, that would have, okay.
Yeah.
Okay, so then that's the action. So it'll, like C4 will fix the axis and just flip the neighborhood over top of itself. Is that
Which action of C4? Okay, yeah.
So,
Yeah.
okay, and then you can see the
Mm-hmm.
action of
Mm-hmm.
order 2 subgroup. Okay.
Well, that one acts trivially as well. You know what? Here's what I'll do. I'll think about that and give it as a problem for today. And then we can try to draw it out and come up with examples. I mean, I definitely see your question. And all I can say is sort of keep coming back to, think of this now completely H equivariantly. This is a fixed point. And so then it's just a question of, is a disk about any fixed point the same or equivariantly isomorphic to the disk about the origin? And that's the real question that I'm asking here. If I look H equivariantly, this is an H fixed point. So I'm asking, is the disk in a representation about a fixed point isomorphic to the disk about the origin? And the isomorphism is described by essentially just drag it along the fixed point line to that. Or it's really, there's an affine transformation that is add that fixed point to every point in the disk, and that's an equivariant isomorphism. So that's the way I'm identifying the two of them. But I think you're right. Drawing a picture that's not sort of too trivial will be a good one, so let's play around with it this afternoon. Now I have an isomorphism that I'm a little embarrassed didn't come up before. If I have something induced, but this guy is in the image of the restriction map, then there's a natural isomorphism between this and this. That in general, if I have G mod H plus smash X, this is equivariantly isomorphic to G plus smash over H, the restriction of X. You should think of this as being like if I cross a G space with G, that completely frees up the action, and I didn't need the action on the space anymore, that the G part completely ate it up. And the isomorphism here is again given by basically multiplication by G. Or it sends a paired GH. Well, you can work it out. It's easier to go from this side to this side and just think of what the identification is doing. Okay, this was the map that I wanted. So what's this tell me? It says that if V is in my universe, then we have a non-trivial map which goes from the zero sphere to G mod H plus. And the reason is because sitting inside this colimit is the V-fold suspension of both sides. Well, that's this map. So it doesn't show up at the first stage. It shows up once I've taken the V-fold suspension. And then everything that contains V is, again, cofinal in everything that contains U. So I get that. I see this map in the direct system.
So is the idea that we just are going to pick all the like cofinal things that we need based on all the subgroups we need, and then that will give us everything? I mean,
I'm not sure I
like
understand.
if G is finite or something, and
Uh-huh.
we can just enumerate all of the, you know, the cosets or by subgroups, or the quotients by subgroups, then we can just pick our universe to have all the cofinal bits.
So the cofinality is a statement about the underlying poset, that I have enough things in it. But yes, what I'm seeing is this condition. This is the thing that I get to vary as I talk about stabilization. And I see that if I have V sitting inside U, such that G mod H embedded into V, then I get an element like this. So I could choose. It's not the case that V is unique. All I needed is a V that this embedded in. Then I would have it. And so it's not the case that the universe is unique. Any universe that does it will work. The cofinality says that no matter what my choice of universe is, provided I have V, then this still works. Yeah?
So yeah, you've been doing lots of the finite groups.
Yeah.
If you tried to, like, if you had like a lattice that was kind of infinite, or like if you had made some other, like a compact Lie group or something, is there anything you'd have to alter here? Or,
Yeah.
there's a few places you might have to like make some.
The thing that you have to remember, so if your group is not compact Lie, and I'm going to also include finite there, then a bunch of the things that I'm going to talk about break down in a lot of ways. That I can embed G mod H into V, but I could do it in ways where it's not sort of embedded as a closed object. Take the example I gave of the integers acting on the real numbers by multiplication by 2. I can embed the integers in that way, but it has an accumulation point at 0. So it doesn't really make sense to talk about the Thom collapse in this case, because I start to worry about what's going to happen as I converge towards 0. But then again, I also couldn't make sense of the representation sphere as a GCW complex there for exactly the same reason. In the compact Lie case, so far everything I've said works mutatis mutandis. What I'm going to want there is that H should always be a closed subgroup, because that ensures that this is Hausdorff. The example to think of is take a circle and embed it in the torus as a line of irrational slope. Then that's dense inside the torus. And, so then the quotient space is in Hausdorff. But if I choose a smooth embedding of G mod H into V, then I again have a tubular neighborhood, and I again get this exact sort of statement. But I have to be a little more careful there. It essentially works the same way, and I still get a collapse map like this. So from those perspectives, none of the things have changed. This isomorphism also didn't care about the kind of group. That actually works. That was just a statement about a group that acted. So you don't have to worry. So I still get this even in the compact Lie case. One other one that I think would be neat but don't know enough about is I could also just take compact groups and ask how much of this goes through for just compact groups. I feel like there's some sort of structure theorem that says compact groups look like inverse limits of Lie groups, and then you can start to understand what happens there and try to build it up. But I don't know. So I'm going to name this element. I'm going to call it the transfer from H to G. And the amazing result, which I'm not going to prove, but I'll just invoke in this case, is the following. If G mod H embeds into my universe, then we have a natural isomorphism X to G plus smash over HY is isomorphic to IH upper star X into Y H equivariantly. So in other words, stably, once G mod H embeds into the universe, induction, which was the left adjoint to IH upper star, is also the right adjoint to IH upper star, i.e. induction equals co-induction. This happens in representation theory. That's why when you look in representation theory, at some point people never talk about co-induced representations. Well, in the finite case. It's because the induced representation and the co-induced representation are naturally isomorphic. Same thing here. Once I've done this process of stabilization, induction and co-induction become naturally isomorphic in this category. This is shocking. I mean, I'm actually just going to say it flat out. This is really surprising. And the reason is, if you just think, this is a wedge of G mod H things. So look back here. This one also was actually fairly surprising. If I took the zero sphere, well, that's fixed, and then I map into G mod H. The only point in G mod H that's fixed is the base point. So if I think of the non-equivariant, or just the ordinary non-stable equivariant maps, the only maps from the zero sphere to G mod H plus are the constant map at the base point. This is saying I have extra fixed points, because I could have thought of this not as the induced zero sphere, but as the co-induced zero sphere, where I have the diagonal sitting inside. And the diagonal, the co-induction is the product of all the things, where I rotate around. So if all of my coordinates are the same, then the group fixes that. That's what I end up comparing this to. So I'm not going to prove this, but the proof isn't difficult. It would just be a little lengthy, and I'm low on time. This map, the one that we just constructed, is one of the natural maps that you use to prove an adjunction. So I have a unit and a co-unit map. We've run into them already in terms of the adjunction for loops and suspension. And this produces one of them. Yeah?
You said natural, but you chose a V here.
Yeah.
Okay.
It doesn't depend on the choice of V.
Okay.
Yes, so there's a few parts that it doesn't depend on the choice of V. In this case, even if it did, I could have chosen V at every point, and that's still natural in X and Y. So, but it turns out that I don't need to worry about my choice of V.
So the adjunction uses the dump class?
The adjunction uses this map. That this one is the, well, I can see this is a map from the zero sphere to G plus smash over H of the restriction of the zero sphere. So that's the map from the zero sphere to the right adjoint applied to the left adjoint. That one's the unit of the adjunction. The map from G mod H plus smash IH upper star X back to X, that's just the act on X map. So that's the natural one, and this is the one that we had to build. So, and it only shows up stably. So let me give a couple of consequences that are really nice, and that the reason you might want to care about these. So, well, first of all, the induction is co-induction is great. But the second is that, well, let me make a definition. So, the Burnside category is the category whose objects are finite G sets and such that the morphisms are, and then, my Burnside category I read it as a script A. So that was an S. So script A between two G sets S and T is going to be the group completion of the set of isomorphism classes of U mapping to S cross T. So when I say the group completion, I mean that I have an addition on this And the addition is disjoint union. So it's not the case that the disjoint union of finite G-sets is an associative operation, but it is the case that the disjoint union of three things is isomorphic to any of the ways that I could pair them. It's not the case that it's commutative, but it's isomorphic to any of the ways I could pair it. The empty set provides the identity element. Yeah?
But are the U's the like open subgroups of G or?
No, U is again just a finite G set that sits over S cross T. So it's the one, and the map is a G map. It's a map of finite G sets.
So the addition is like is the set of all the maps from all the G sets U into the product
So yes,
under that addition.
I take the set of all isomorphism classes of U over S cross T. And then I endow that with an addition by saying that U over S cross T plus V over S cross T is U disjoint union V over S cross T, with the obvious map, using the disjoint union as the coproduct.
Isomorphism is the triangle thing, right?
Exactly. And so then I group complete that. So what I want to observe is that this is symmetric in S and T. So the category is naturally self-dual. So A is isomorphic to A op, where on objects I just send S to S. And I use the fact that A of ST is the same as A of TS. In fact, it's equal to A of TS. But I get some other things. I get that A of ST is actually the same as A of S cross T point is the same as A of point S cross T, etc. So I get lots of things like that. Now the theorem, which is due to Siegel and Tom Dieck, although the formulation I'm going to give is due to Tom Dieck, is the following. The map, well, there's a map, a functor, from the Burnside category to this category. It's the category which I'll call SW for Spanier-Whitehead, and this is our, and a G, which is finite GCW plus stable maps. And I'm going to do stable maps for the complete universe. That sends a map S to the suspension spectrum, to S plus, which is in fact a finite GCW complex, and then sends a map. Well, this is a functor, or extends to a functor. And is a fully faithful embedding. So what do I mean by that? I mean that using this equivalence, I can see the following, that maps in the Burnside category from S to T is isomorphic to the stable homotopy classes of maps from S plus into T plus. So this is nice. We have lots of extra structure, a huge amount of extra structure. And it's arising from this beautiful algebraic category namely just finite G sets and correspondences of G sets. And then out of that, I produce this stable collection of maps. So I want to give just a hint of how this shows up. So, sketch. So first of all, since wedge is the product and coproduct, well, the finite and coproduct, it suffices to show this for S is G mod H, T is G mod K. Because S split as a disjoint union of things, disjoint union went to a wedge, and then maps out of a disjoint union is the product, or maps out of a wedge is a product, maps into a wedge, also the product, everything inside's finite. So all I have to do is understand this case where I have a single orbit. So now I can use this. And I'm going to leave it up for now. So part 2. If I look at maps from G mod H plus to G mod K plus, well, by this adjunction, this is the same as K equivariant maps. I'm sorry. Into, well, just the zero sphere. But now, this guy is actually in the image of the restriction. The zero sphere is IK upper star of the zero sphere. So I've used here that induction is the right adjoint to the forgetful functor. Now I can use that the forgetful functor has a left adjoint, which is also induction. So this is G plus smash over K, IK upper star, G mod H plus, into the zero sphere. And then via the isomorphism that I just erased, this is G mod K cross G mod H plus into the zero sphere. I could have also run this the other direction, said, oh look, the left-hand side is induced. Induction is the right adjoint, is the left adjoint to the forgetful functor, so then use that approach. And I would have learned that this is the same as maps from the zero sphere into G mod H cross G mod K plus. Same sort of setup over here. That when I want to understand maps between any of my two finite G sets, all I have to do is really move them to the same side. In particular, it'll suffice to determine maps from the zero sphere into a single G mod H plus by part 1 again, but this is the same as stable maps from the zero sphere to the zero sphere. And now this is a computation. It's not a difficult computation. So the last part we have to show is that maps from the zero sphere to itself is the maps in the Burnside ring from a point to itself. And this is sometimes called the Burnside ring of G. It's isomorphism classes of finite G sets.
Did you mean to switch to G? I'm not waiting for it.
Yes. So, by induction on the order of G, it suffices to compute that. Okay. So, there's one thing that I've swept under the rug here, and that is I said that it extends to a functor. So I should describe for you at the very least how I'm supposed to produce a map. But actually, this analysis is really what's giving it to me. Let's say I have some U over S cross T. Well, I can project onto either the factors. And this gives me what's more traditionally called a correspondence, so a map from U to S and a map from U to T. So let me give them two names. So now I want to produce a map from S plus to T plus associated to this U. And so the way I'm going to do it is I'm going to say, well, let's think of this map as the composite of first a map from S to U, and then a map from U to T. And in fact, I could explicitly write it as the composite, where I would insert a little just base point, and this becomes a map from S to the base point that's given by U, and a map from the base point to T that's given by U, and when I compose them, I get this. So I can explicitly do it that way. But let's just figure out how to write this as a stable map from S to U. And the trick is simply stable maps from S to U. She used a different U. Well, tracing through this argument, stable maps from S to U is the same as stable maps from U to S. First, I move everything to one side. Then I move the other factor to the other side. So it's that same, already this category has the self-duality for the finite G sets. The stabilization of this map, well, F sits inside there, as coming from the very bottom part of the colimit. So how do I produce a map here? Well, I just trace through. How do I get this map G? Well, the map G is actually kind of obvious. If I have a map from U to T, then I stabilize it, and that gave me a map from a stable map from U plus to T plus. So this goes to the composite G composed with this F upper star from S plus to T plus. And I'll leave it to you to check, which isn't difficult, but it's a little bit tedious, to check that this actually is a functor. So in other words, that it plays nicely with the composition, that it didn't depend on the isomorphism type of U. All right. So I'm going to make one final remark. So when I do all of these, I like to have in the back of my mind, how would I compute with them? So a contravariant functor which of course is the same as a covariant functor. from my Burnside category to ab is a Mackey functor. And then really I should say a contravariant additive because it doesn't, no reason not to. So this is a generalization, or it's the stabilization of our old coefficient systems. And the important thing about Mackey functors is that the homotopy groups, the stable homotopy groups of anything, is a Mackey functor. And then I'll just write what a generic one for C2 looks like, and I'll be done. So if X is in the Spanier-Whitehead category, for G, then pi k of X, remember we had a coefficient system version of this. So this is going to be stable maps from whatever I put in here plus smash the k-sphere into X. This is a Mackey functor. So once I've stabilized, not only are my homotopy groups abelian group valued, or in fact the homotopy class of maps between any two objects, not only are they abelian group valued, but also they're Mackey functor valued. It's canonical extra structure that comes along for the ride. I have my restriction maps, which are the same ones as before. Namely, if I have a G equivariant thing, I can forget that it's G equivariant and just remember that it's H equivariant. That provides the contravariant maps. That provides the value associated to these maps. It's these ones, the covariant part, that needed the stabilization. That needed, in fact, that I was stabilizing along a complete universe. So I would get all of them. And so here's what I'll finish with. Back to G is C2. This is what a generic Mackey functor looks like. You specify its value at C2 mod C2. You specify its value at C2 mod E. You have a restriction map. And then you have now the transfer map. And we had our automorphism of order 2. And the important thing is that the composite of the restriction and the transfer, let me call this gamma, is 1 plus gamma. So in fact, the way I've drawn it's overdetermined because I could rebuild gamma out of just the restriction and the transfer. Everything in sight, that when you do computations, you'll see things like this. These are the coefficients for homology. They're the same as the coefficients for cohomology. These are the values of the homotopy groups. Stable obstruction theory, all of it takes place in this world. This produces tremendous constraints on what can happen. It's very easy to write down coefficient systems that don't extend to Mackey functors. So there's a lot that shows up here just because it's much more rigid than you would have necessarily expected. All right, I'm again over time, sort of systemically, and so I'll stop here, and thank you.